An inverting amplifier is a type of operational amplifier, op-amp, circuit configuration commonly used in electronics to amplify an input signal while inverting its polarity. Here are the key characteristics and principles of an inverting amplifier. Basic configuration. Input configuration. The input is applied to the inverting terminal of the op-amp. Feedback configuration. Negative feedback is employed, where the output is fed back to the inverting input. Gain. The gain of the inverting amplifier is determined by the ratio of the feedback resistor, RF, to the input resistor, R. The formula for gain, AV, is given by negative RF by R, where AV equals RF/R. Polarity inversion. The key feature of an inverting amplifier is that it produces an output signal that is 180 degrees out of phase, inverted, with respect to the input signal. Operational principles. Virtual ground. Due to the high input impedance of the op-amp, assumed infinite in ideal cases, virtually no current flows into the inverting input. As a result, the inverting input is considered a virtual ground, maintaining a voltage close to zero. Current flow. The input voltage, Vn, applied to the inverting terminal sets up a current, In, through the input resistor, R, according to Ohm's law, Vn equals IR. Feedback mechanism. The op-amp adjusts its output voltage to maintain the inverting input at virtual ground. The output voltage is fed back to the inverting input through the feedback resistor, RF. Output voltage. The output voltage, Vout, is determined by the current flowing through the feedback resistor. The relationship is given by negative RF times Iout. Characteristics and considerations. Inversion. The output is inverted concerning the input signal. If the input signal increases, the output signal decreases, and vice versa. Gain control. The gain can be easily controlled by adjusting the values of the feedback resistor, RF, and the input resistor, R. Commonly used. Inverting amplifiers are widely used due to their simplicity, ease of design, and predictable behavior. Single supply operation. In single supply configurations, a bias voltage is often introduced to ensure proper operation. In summary, an inverting amplifier is a versatile and widely used circuit configuration that provides controlled signal amplification with a predictable phase inversion. Its virtual ground concept and straightforward gain control make it a practical choice in various electronic applications. The inverting amplifier is one of the basic op-amp circuits. Assume that the input impedance of the op-amp is infinite. This means no current flows into or out of the op-amp inverting input. Since the op-amp forces the voltage at the two inputs to be the same, the inverting input, minus, also appears to be ground. This is commonly referred to as virtual ground. In addition, according to Kirchhoff's law, all currents flowing into the node must also flow out of the node. The input voltage sets up a current. In equals Vn by Rn. The current out of the summing node is equal to the input current. In equals Iout. The voltage across the feedback resistor, RF, is, therefore, minus Vout equals RF times Iout. The voltage is negative, relative to the input voltage, since the current is flowing out of the node. This is why the circuit is referred to as an inverting amplifier. Note that the input voltages will be scaled by the values of the input resistors. The major error sources in this circuit are the offset voltage and the bias current of the op-amp. The offset voltage will affect the apparent voltage at the inverting input. It will no longer be 0V. The bias current will cause an error in summing the currents since a small current will be flowing into or out of the op-amp's input. For AC inputs, there will be the limitations of the bandwidth of the op-amp. The input impedance of the amplifier circuit will be the value of the input resistor. Remember that the other end of the resistor is at virtual ground. The above discussion is based on bipolar power supplies. If single supplies are used, the ground is replaced by the reference node, which has a voltage level of Vref, which is typically half of the supply voltage. The input and output voltages are then referenced to this voltage rather than ground. The input current becomes IN equals VN minus Vref by Rn. Output becomes Vref minus Vout equals Rf by Rn times Vn minus Vref.